So, welcome to Biomaterials. Today we're going to talk about stress concentration. And what do I mean by stress concentration? Well, basically, in a lot of earlier lectures, we might have been, taking something and saying, okay, we're applying tension to it, and we assumed that basically, we said stress was force divided by area. And when we were sort of pulling on this, we assumed that stress was distributed equally. Every little bit of the cross section of this rubber band that I'm pulling on, we assumed that each of those little bits, all of those little bits, had the same sort of intensity or the same concentration of force, kind of passing through, transmitted from one side to the other. But spoiler alert, that's not always the case. So the idea with stress concentration is stress is not always uniformly distributed not always uniformly distributed over the cross-sectional area. Right? It's not always uniformly distributed over the cross-sectional area, and when it's non-uniformly distributed over the cross-sectional area, this might mean that at least at some local places, things might break unexpectedly. Things might break unexpectedly. So what does that mean? Well, basically, from an engineering standpoint, the naive approach is basically to say stress is uniform, and stress is equal to force divided by cross-sectional area. And when we're sort of considering stress-strain curves, if we sort of say, hey, here we have our stress-strain curve. If you remember, we had these features of the stress-strain curve. We basically had a yield stress. We might say, hey, we're going to set this equal. We might set this, whatever stress we want equal to our yield stress, and this, for example, would allow us to estimate what is the max safe force that our rope can support, that a rubber band can support, or something like that. Or it might say, hey, what is the minimum cross-sectional area to keep sigma, to keep our stress much less than, or maybe not necessarily much less, but at least less than the yield stress. But if our stress is uniform and we sort of set our force divided by cross-sectional area precisely equal to the yield stress, in real life, if some stress is higher than the sort of average stress and some is lower, i.e. due to non-uniformity from stress concentration, and some is lower, then it might fail by locally exceeding the yield stress. And oftentimes it's not like the whole part needs to fail. Even if just one part of the system fails, then we can sort of have a runaway effect, right? If you imagine I'm pulling something and some crack starts, and that crack can then propagate all the way through the device, even if that failure starts locally, that failure can become systemic real fast. And yeah, that's bad. Definitely want to avoid that. So as engineers, what we need to do is at least develop some physical intuitions about when we're going to have stress concentration and when that stress concentration is going to be worse. So we want to develop intuitions, when will this be really bad? And that's basically what today's lecture is going to focus on. At least developing some qualitative intuitions about when stress concentration is really bad. So today is going to be qualitative intuitions. And outside of the scope of this class, you can use computer software to develop quantitative. So computer software, for example, you might have heard of finite element analysis, for example, with software like ANSYS or SolidWorks or Abacus or something like that. There's computer software that basically can mathematically predict, saying, hey, if I have this weird geometry and I apply forces to it, I can get quantitative predictions of stress distribution. But this is kind of outside of the scope of what we're going to cover today. So today we're just going to get some qualitative intuitions for when we might observe appreciable amounts of stress concentration in various geometries and situations. Prepare yourselves for a live demo. Here, I have two pieces of plastic bag. They're just like I went to the grocery store. I came home with, actually I did curbside pickup, but I got some of my groceries in plastic bags, and then I just cut two strips of plastic bag, and to sort of get a sense of, obviously these two strips are slightly different from one another. Here I have one piece. Oops, marker's bad. So I have one piece that's wide, but I don't know if you can see it right here. Maybe I'll try to show a little more clearly. But if you look, there's a little, I'll try to put something dark behind it. If you look, there's a little tear. It's a little tear, a little crack that I kind of got started in the plastic bag right here. So it's a little cut. Took scissors and kind of snipped it right here. And the second one doesn't really have any cuts at all. I tried to keep those edges like nice and clean and smooth. So I have these two pieces right here. And what am I going to do? In just a moment, I'm going to apply some force. I'm going to apply some force to try to pull them apart. And when I was creating these two strips, I was very careful to basically have this width right here and this width right here. So, I mean, obviously this one is much wider than this one. But even given the little bit of a clip here, let's call this width W1, and we'll call this width W2. Even given the cut, W1 is bigger than W2. So if we were thinking, from a naive approach, from a naive approach, which one has more stress. So let's do pause and ponder. From the naive approach, of uniform stress, which one has a higher stress? Which one would we anticipate has a higher stress value? And then I want you to think, pause and ponder, which one will be easier for me to break? And in fact, if you want to, before I go ahead and do this with your video, you probably have a plastic bag lying around somewhere in your house. Go ahead, recreate this experiment yourself, being careful with the widths and all that stuff. Length doesn't make too much of a difference here, but the widths, these widths here. So take a moment now, pause and ponder, which one has, from the naive approach, which one has the higher sigma? Well, from the naive approach, this would actually predict this one has the higher sigma, right? If W2 is less than W1, then the same force divided by a smaller cross-sectional area, the naive approach would predict this one. But, spoiler alert, which one's going to be easier, in real life? Which one's going to be easier to break? It's actually going to be this one due to stress concentration. And I'll show that right now. So right now I'm going to take this one, I'm going to break it. Okay, all right, finally broke. Now I'm going to take this one and I'm going to break it. And this one tore like super easy, right? We can see it's that tear started right at the crack and then just shot right across, easy peasy, right? Whereas this one, I needed to stretch it out and stretch it out and stretch it out, and it basically kept stretching and stretching and stretching because that stress was uniform and because it was distributed evenly. There wasn't some weak point that just gave rise to the whole thing breaking. So in real life, it was easier to break the one with the crack, even though the naive approach would have predicted that this one breaks first because it has a smaller cross-sectional area. So what's going on? Well, let's just imagine that you were a magical being and that you could see force, or you could see stress. Well, if you could see stress, then it would reveal what's going on with stress concentration. So in the small one, in the narrow cross-section, there's basically no real place for stress concentrators. So I have this force here, I have this force here, and you can basically imagine those forces sort of being transmitted via sort of a bunch of parallel lines. And they're basically evenly spaced. And that basically means that stress is uniform. But if you imagined I took this one and I applied these forces here, well, down here, far away from the crack, this stress would actually be lower than this one. So, even if I choose the same number of lines, right, there was 1, 2, 3, 4, 5 lines, 1, 2, 3, 4, 5 lines here, and 5 lines here, here you can almost imagine these lines as sort of like a force density, and a force density is basically stress. This is basically low. There's a low stress region right here, but stress can't just jump over the crack, right? If there's a crack there, this side right here cannot really apply any force to the other side. So those stress lines, instead of hopping over the crack, they need to take a detour around around that crack site. So what happens is, because they take a detour around that crack site, even if in these regions we have low stress, we basically have this point, this region right here at the crack tip that leads to stress concentration. So right here at this crack tip, because these sort of stress lines bunch up, we get stress concentration. And that means that locally at this crack tip, the stress is actually much higher than the average stress out here, and in fact even much higher than what would have occurred if the cross-section were fully uniform. So basically we get this stress concentration here, and it basically, the crack yields right here, and then that crack ends up propagating through the whole material. So what's the key takeaway here is we get stress concentration at sharp interior corners. And you can see this in your everyday life. So, if you're walking down the street, let's say here's the sidewalk, and you might see, let's say, a stop sign. Let's say there's a stop sign right here. Right, there's a stop sign right here. Oftentimes those stop signs have square posts, square cross-section posts. And those posts might be set into the concrete here. And basically, if you look in the concrete, a lot of times they've basically, poured the concrete around the post or something like that. There's basically a square hole. And if we think these corners of the square hole, right, these corners of the square hole are basically doing the same thing as what this crack or this snip in our plastic sheet did. And if you look at the corners of the square hole, oftentimes what you'll end up seeing is you'll basically see these cracks that basically start radiating from the sharp interior corners. So like every time you're walking down the street, just look at the bottom of these square holes, and boom, without fail, every single time you'll see cracks. So as an engineer, what do you do? You basically want to round off. So the solution is basically to round off or fillet into sharp interior corners. Right, so for example, if I had some piece that looked like this, instead of having a sharp corner right here, what I would do is I would have some material that kind of bridges and sort of fills in that gap right here to allow, stress to kind of round that bend more easily. So instead of having a sharp corner right here where all the stress bunches up, it can now sort of all pass smoothly around the sharp interior corner. So if you're designing parts to be injection molded or 3D printed or whatever, you want to make sure to avoid having sharp interior corners in your design. Let's now take another example of stress concentration. So another case where you get stress concentration we also observe stress concentration at typically at material mismatches. and in particular at material mismatches in their modulus of elasticity. So if I try to have a stiff material next to a very compliant material, we oftentimes observe stress concentration at the interface. So if we have a stiff material and a compliant material, we observe stress concentration at the interface. So material mismatches at the interface. So what does that mean here? Well, we can sort of look at this live demo that I have here. So I basically have one, again, this is a strip of just a grocery bag here, and then this other one, I've reinforced it by taping a metal piece to the very center of this plastic right here. So I'm gonna take one, and I'm gonna pull this one, and I'm gonna pull this other one, and I want you to pause and ponder, which one is going to be easier. So which one will be easier? The quote-unquote reinforced one, with the metal, or the plastic only? Right, and maybe a naive person might say, oh, there's metal in there. That means it's going to be a lot stronger. And that one's just plastic. How could the just plastic one possibly be stronger? Well, pause and ponder, think, which one's going to be easier for me to break? Well, hopefully you've had a chance to pause and ponder. Let's do it now. I'll take this one. All right, take some force. All right, it finally snapped. All right, now I'm going to do this one. Whoa, easy. And basically what happened? Well, it didn't even break at the metal. It actually broke at the tape plastic interface. And it turns, there was basically a material mismatch. I mean, there was definitely a material mismatch between the plastic and the metal, but there was also a material mismatch between the tape and the metal. And the tape and the metal, it basically started a tear right here at this corner where the plastic bag interfaced with the tape. So what's going on there? Well, let's take a look. I mean, I know we can't see stress with human eyes, but we can kind of make a prediction of what's going to happen. So for our reinforced one and our plastic only one, let's look at them. So imagine I have my plastic only one, right? I take my forces, I apply my forces like this, and I get my stress lines. I have my stress lines going like this. Then I have my reinforced one with a very stiff material occupying the middle of it. Well, what happens when I apply this force is the plastic starts to deform, but the stiffer material in the middle does not deform, right? So basically the plastic is like, hey, let's stretch, let's stretch, let's stretch, let's stretch. But the stiffer material doesn't deform, and that leads to non-uniformity in how that stress is distributed through the material. So, and exactly how that stress is distributed depends on sort of the mismatch between stiff and compliant. So if the orange, so let's look at two cases. One case, which is what was here. So this is the case where the orange is more stiff. And then later on, we'll look at a case where the orange is less stiff. So if the orange is more stiff than the surrounding green material, it basically requires more stress to deform the same stretch. As you can imagine, I'm stretching the green wants to stretch, the orange doesn't want to stretch, so basically the orange almost sucks in some of that stress. So what's going on here is, initially we might sort of have our evenly spaced material, we might sort of have our evenly spaced stretch line, but because this orange requires more stress, it almost sucks in the force to be transmitted through it, and then it kind of continues back being uniformly distributed. But what goes on here is on the way into the material, we get stress concentration. So as these stress lines are sort of getting kind of sucked into the stiff material here, we get stress concentration. So we get stress concentration kind of as it approaches it. In a sense, the opposite is true, but with an equally bad conclusion if the orange is less stiff than the surrounding materials. And you can almost imagine it like in the extreme case where the orange is a whole. If the orange is a whole, it kind of behaves almost the same way that this crack did. If the orange is a whole, the stress sort of gets deflected around it. Ooh, can't touch this. Oh, can't touch this. And I basically get stress concentration. I get stress concentration at the sides. So regardless of whether the insert is stiffer or less stiff than the material around it, I still get stress concentration. And you can imagine that this has problems in bioengineering. So pause and ponder now. When might stress concentration, due to a material mismatch, be problematic in bioengineering? Well, there could be any number of cases, but the case that's most prevalent to me is with bone screws. So if someone has, let's say, a femur fracture, let's say if someone fractures their femur, oftentimes what surgeons will do, is they'll put plates up against, maybe on both sides of the bone, but at least on one side of the bone. And then what they'll do is they'll put in some screws through holes in the plate and basically to anchor the plate against the bone. So they'll put screws through the plates and do that. But the stiffness of most metals is usually an order of magnitude or two above the stiffness for bone. So when we're applying forces to the femur, and those forces need to be essentially transmitted from the bone to the screw, from the screw to the plate, from the plate to the other screw, and then from the other screw back through the bone, because the metal and the bone have a horrible stiffness mismatch, we often see failures at the bone screw interface. And there's a lot of clever material science that actually goes into either coatings or treatments or something like that to basically make these screws less stiff. And in fact, a lot of times people don't want to make these screws out of steel because steel is very stiff. They would much rather actually choose a more compliant material. So basically we want to choose compliant, not in a sort of regulatory compliance sort of manner, but like a physically compliant screw material. So actually metals like magnesium are often far better than steel, even though you might be like, oh, steel really strong. Yeah, steel's strong, but also steel's really stiff, so it exacerbates this stress concentration effect. Magnesium, it's still stiffer than bone, but it's much less stiff than steel, so it sort of lessens this stress concentration effect. So for example, magnesium is actually a really good metal for bone screws because it lessens, because it's less stiff, so it lessens stress concentration at the bone screw interface. So thanks for concentrating on this lecture with me. I hope it wasn't too stressful, and thanks for good luck with your study of biomaterials.